Welcome back, and like I said before, into the break, we're now going to look at the electromagnetic spectrum, and this is going to be lots of fun. Now guys, when you do the spectrum, it's really important that you understand the way the spectrum works, and you know the different parts of the spectrum. You don't have to know specific values to the spectrum, but you do need to know how the spectrum works and where it goes from. Now, I'm hoping you all have some sort of diagram of the spectrum, and I have one on the screen where I'll show you which shows you the basic parts of the spectrum, starting from radio waves, which are quite long, low frequency waves, and it moves all the way to gamma rays. So we look at radio waves, microwaves, infrared waves, visible waves, which is light, ultraviolet, X-ray, and gamma. Now we're going to look at each of those in a little more detail. I'm going to give you values for frequency and wavelength, but the honest truth is, grade 10s, is that they're an indication of where they stop and start, but the boundaries aren't exact. So it's not like I'm going to go from radio waves, and as soon as the wave changes from 10 to the 8 hertz to, 10 to the 7 hertz to 10 to the 8 hertz, it's now become a microwave. There's a little bit of a fuzzy, it's like looking at a rainbow where the colors just sort of blend into each other. It's the same concept, okay? So what we're going to do is we're going to look at the electromagnetic spectrum, and we're going to do it in bits and pieces, and you're going to need to just stay with me, okay? So if we look at the electromagnetic spectrum, the first thing we're going to look at in the spectrum is the fact that we have a whole bunch of things. I'm just going to go back a little bit. And the electromagnetic spectrum is made up of 7 distinct points, okay? We have radio waves, microwaves, infrared waves, visible light, ultraviolet, X-ray, and gamma rays. Let's now think about, we're going to start at the beginning, and we're going to look at radio waves, okay? Now, radio waves do exactly what they say they do. That's what's responsible for us being able to hear radio, okay? They're very long wavelengths, so it's the very first part of the spectrum. They're very long, okay? Those radio waves have high, big wavelength, short frequency. So if we look at a radio, which is a good example of one, their wavelength is between 1,000 meters and 0.1 meters. That's a kilometer to about 10 centimeters. Their frequency, though, is very low in relationship to the rest of the spectrum. I still know 10 to the 6 hertz is very high, so is 10 to the 10, but it's actually quite low once you get to the rest of the spectrum. And those are the waves that are responsible for us hearing radio, okay? Not only that, but once we get past the fact that we use them for radio, so radio waves are used for all sorts of things, okay? Now, one of them is for very, very, very big telescopes. In fact, the SKA, the Square Kilometre Array, which South Africa is still bidding for and hopefully we get, is a whole bunch of telescopes that look at the world outside, look at the stars in the universe, and pick up radio waves that are being transmitted from stars and all sorts of other celestial bodies from far, far away. And these telescopes are extremely big. They're big, big dishes. Those dishes then are able to pick up these radio waves, and they translate that into images that we then make, which is actually really nice. So we use these huge, big telescopes. Another example of one, which is they're just ginormous, these big plates. It's almost looking like a satellite dish like you use at home in order to get your DSTV. Okay, so we use radio waves all sorts of places, specifically for looking at the universe out there. The next part of the spectrum is microwaves, okay? Microwaves come after our radio waves, so there they are. They have a slightly shorter wavelength, slightly higher frequency, and I know you're all going, oh, we know microwaves. Of course you do. Microwaves are used for cooking. So we love microwaves because it's a good place for us to cook. So there we go, as an example of what microwaves are. They range in size now between 15 centimeters and 0.1 centimeters, so they're getting much shorter. But look at the increase in frequency. They go from 10 to the 10 hertz to 10 to the 12 hertz. That's quite a big difference from radio waves, which started at 10 to the 6. So microwaves we use for cooking, for all of that sort of stuff, which means they're also slightly hotter when it comes to the heat they produce, okay? Microwaves are starting to become a little more dangerous for us. you all know that when they cook food, they're actually heating up the food. They excite the molecules inside the food, and we get that's what makes it nice and hot. A klystron, which is the diagram you can see on the screen at the moment, this is a very special little, it's not very little, it's quite a big piece of equipment which is used to produce microwaves in industry when they need to use it for experimentation and that sort of stuff, okay? We don't want to have one of those running around at home because it can get quite dangerous, so we'll ignore those. Microwaves are also responsible for satellites and that sort of stuff, so we use them in all sorts of different environments, and it's very important for us. The next wave we're going to look at is infrared. Infrared, you're going, oh wait, no, we've heard that term before. Of course you have. Okay, in fact, often you'll see infrared imaging. Infrared imaging is when you see those wonderful images and you see a person and they look like they're red and blue and yellow and green and all sorts of things. It shows the heat that a body produces. Every single body in the universe, every object produces a certain amount of heat. Sometimes that's quite significant, sometimes it's not. It all depends on what it is. Your lights at home would be producing a lot of heat. Your body produces a lot of heat, so that's why we can see people when it's infrared. It's a nice, interesting thing to use. We can't see infrared. Okay, it's not something we can physically see with our eyes, so we use special equipment for that, okay? So with infrared, we notice that we're starting to get, in fact, there's a very nice image showing you infrared. The red parts in the image are where this person is hotter, okay? His head, it's blue, it's not quite so hot. Now the wavelength is now changing from 10 to the minus 3 to 10 to the minus 6 meters. Now they're getting really, really small. The frequency, 10 to the 12 hertz to 10 to the 15 hertz. Much, much larger, okay? It's an approximation. Getting much, much bigger. So it makes it a lot easier for us to see the difference. And I'm hoping what you're noticing here, grade 10s, is as the wavelength is getting smaller, the frequency is getting higher. Okay, so as the wavelength decreases, the frequency increases, and we're quite excited about that because we've seen a nice change. Now, what you're going to see is, and I'll show you, and you can see it on the graphic that I've got at the moment, is that as the wavelength gets smaller, you can see they're getting closer and closer together, the frequency is increasing. That's a very, very important relationship for you to get, grade 10s, because in terms of the spectrum, we can either have the spectrum in terms of increasing wavelength or increasing frequency, so be very careful when you look at that. The further along we go, the more we realize short wavelength, high frequency. The next part of the spectrum that we're going to look at when we get there is the visible light spectrum. So here we have visible light that ranges in our nice little rainbow: red, orange, yellow, green, blue, indigo, violet. Okay, rainbows are always in that order. There is absolutely there's no exception to that ever. And an interesting little fact for you is Sir Isaac Newton, when he's accredited with finding our rainbow and deciding what the colors are and being the first one to be able to disperse light into the rainbow, he couldn't actually ever see all 7 colors. He couldn't physically see all 7. He wasn't able to distinguish them, and it's actually really hard in the blue, indigo, violet section to distinguish them. But he knew there would be 7 because of what he believed in, and that was just what he decided, was that there would definitely be 7 colors, which is actually quite incredible if you think about it, that he knew that there would be 7 colors to the rainbow. And we will never know why he knew that, but he did. So we're quite excited. Of course, now we can prove that. Let's go on to UV light. Now, UV light becomes a very short wave, high frequency. UV light is extremely dangerous for us, okay? This is what causes skin cancer. UV light, and you're going to see in a second, and I just love this graphic because this is a plant under UV light. It's quite interesting. Its wavelength ranges from 10 to the minus 7 to 10 to the minus 8, very, very short. 10 to the 16 to the 10 to 17 hertz as its frequency, and UV lights are often used in clubs and at concerts and stuff, and I'm sure you've all been in UV light. We also call it black light in theatre, where if you have white on or anything like that, it glows in the dark, and it's actually quite interesting to see. It's because of the interaction of the light and the colors and the chemicals in the clothes and stuff that you're wearing. So here, this is actually a plant that's been shown under UV light, and you can see the different colors that you get, and it's actually quite fun to watch. UV light can be used for all sorts of things. And in fact, UV light is split into 3 categories: UVA, UVB, UVC. Now, these 3 variations of UV light are the things that are responsible for ozone and that sort of thing. We'll come back to that in a second. What else we use UV light for is when we look at scientists. I'm sure you've all watched CSI, you've watched those programs, and they spray something on the wall, and they go, oh, I wonder if there's blood. They spray something, and out comes the UV light, and then you see it glow. Okay, it's luminescent. It glows in the UV light. That's a very important usage of it. Another use of it is when shop owners scan money. There is a ultraviolet strip put into our money to stop people from forging it. That's important because we know forged money is a very bad thing. So every currency in the world has these, and that's often shop owners will have those little machines that they'll scan their money in. And recently, in the about a year ago, there was a whole scam about the 200 Rand notes because they were becoming quite easy to forge. And for a long time, shop owners wouldn't take 200 Rand notes because they were being forged. Okay? And if you got one, it was a bit too bad because you were hoping the bank wouldn't give you one. But they scan it under a UV light to check that it's actually a genuine note. So when it's scanned, it glows in the dark. That is a example of where we're using the fact that something will glow in the dark for a chemical test, okay, where we use UV light. Nice way to test for stuff. It's quite interesting when we look at the forensic world. Next part of our spectrum is X-rays. I am hoping that none of you have had to have an X-ray. I have. It's not that painful, but at some stage we might. X-rays can be quite dangerous, though. They have a very, very small wavelength between 10 to the minus 8 and 10 to the minus 11, and high frequency, 10 to the 17 to 10 to the 21. I'm not 100% sure what this is an X-ray of, but it looks like it's a series of legs, okay, where you can see people have had pins put in their legs, and you can actually see where they are. The point of an X-ray is that it is able to penetrate the human body. So it can go through flesh and organs, and then it gets absorbed by or reflected off bones and hard objects inside the body, which is why we get this white part. It's reflected back off a plate, which then takes a photograph, essentially. It is very, very dangerous. And in fact, if you're pregnant, for the girls, you're not allowed to have X-rays because it can damage your baby. So we don't want to do that, okay? You also don't want to be living in an X-ray. In fact, if you've ever gone for an X-ray, you'll know that the technician who takes the X-ray sits in a little cubicle, shielded, and he has lead shielding so that he doesn't get it, or they don't get affected by the X-ray, because long-term exposure can be very, very bad for you. We're going to show you another X-ray in a second. Of course, we can take X-rays of all sorts of parts of the body, and they show us it's what they use for clean breaks. This looks like a dental X-ray, I think. It's a person's head. So when you go to the dentist and they take X-rays of your mouth, it's for them to be able to see what's happening with your teeth. As you guys get older, you'll realize that your wisdom teeth can become a problem. Your dentist will take X-rays of your teeth to see when your wisdom teeth are coming out, if they are coming out, and if they need to actually be removed, which we don't want ever to happen because it's not fun. Okay, so we have X-rays. This one is of dentals. It's showing the teeth quite clearly in your X-rays. X-rays we use at airports, go through X-rays machines. They go and X-ray your bags, and you have to take your laptops out and your iPads, and you have to put your phones on things, and it gets very exciting. It gets very annoying after a while. Actually, last part of the spectrum, gamma rays. Now, gamma rays are extremely dangerous. Very high frequency, very low, very, very small wavelengths. So we have our gamma rays range between 10 to the minus 11, 10 to the minus 15, and 10 to the 21 hertz, 10 to the 24 hertz for frequency. That is extremely high, okay? Now, what that means is gamma rays are very, very dangerous. Gamma rays, if you're exposed to them enough, can kill you. Now you're going, oh, but we get them from the sun. Yes, we do. But we don't get them in concentrated bursts. Okay, so we're not exposed to them like we would be if we're looking at something that's nuclear or radioactive. So gamma rays really come from inside our nucleus of an atom, and inside that nucleus a reaction happens and it spits out a particle which gives us gamma radiation. It's a little difficult to see, but if you watch on the screen you can see that we have an electron. It's an atom that's getting excited, and what's happening is it's shooting off bits of gamma rays. That's what you can see on the screen, the little wave that's coming off, that's the gamma ray. Gamma rays are dangerous, but we can use gamma rays to do things like sterilize medical equipment because it kills bacteria. It'll be gone, okay? Which is a good thing. We like it to be gone. We don't want the gamma rays, okay? Because then we don't want the bacteria on our sterilized equipment, so we use the gamma rays to get rid of it. But we need to make sure we are protected from the gamma rays, okay? Why is this important to us? Because when we look at our spectrum, and we go back to our diagram, the smaller the wavelength here, the more dangerous they become. And in fact, what we say is, remember we said earlier that light can behave as both a wave and a particle. What scientists have realized is that when we have very long wavelengths, like the radio waves, these waves tend to behave more, oh, and we've got that in double, let's try not make that in two different colors. They have a wave nature, all of these. They behave like a particle sometimes, but not very often. So we're not going to find them doing the same sort of thing as particles would do, just because they're very, very long. When we get to the other end of the spectrum and we start looking at ultraviolet, X-rays, gamma rays, these tend to have more of a particle nature. So they tend to behave more like particles because of their high frequency. That means they're able to do more damage. Gamma rays, when these gamma rays come in contact with a human body, for example, because they're behaving like particles, those particles do damage to our cells and the nucleus of our cells and all sorts of things, and they start to erode them. Very, very dangerous for us, okay? We don't like that idea. That also means when we're talking about things like getting sunburnt, that whole ultraviolet radiation issue, okay? And if you've been listening, if you watch TV, listen to the radio, people often talk about the fact that we need to be using sunblock, we need to be protecting ourselves. Of course we do, because ultraviolet radiation is extremely dangerous for us. Ultraviolet radiation actually has three parts. We're going to look at this now in a second. And because it can act like a particle, there are parts of ultraviolet radiation that actually penetrate our skin and start to damage our skin. Okay, so let's actually look at that, shall we? Ultraviolet light gets separated into three parts: UVA, UVB, UVC. You don't often hear about UVC though, but let's look at it. Now, when we look at these three parts of the ultraviolet radiation, they all come from the sun. That doesn't change, okay? UVC is very special because it can be absorbed by the ozone. So we have a picture of the dermis. UVB comes along, gets through the ozone layer, and can penetrate just the top layer of our skin. That eventually tans us. UVA goes all the way through the dermis to the bottom layers. When it gets to those bottom layers, that's where it starts to do damage, okay? That is where it starts to cause things like skin cancer. All right, so UVC gets absorbed by the ozone, and we need it to be absorbed by the ozone, so we want to make sure our ozone's there. UVB comes just the top layer. It's UVB that makes us go brown, or darker as the case may be. Or if you, like me, no, just red, okay? I cannot go brown. I do not have that ability. UVA is what penetrates the skin, goes through past all the skin layers, and that's where we start to get skin cancer and skin damage, which is obviously what we need to prevent. That means ultraviolet light has the ability to penetrate the skin. Ultraviolet light comes before X-rays. X-rays have a higher frequency, which means they can penetrate even more. And we saw that in the diagram, because with X-rays, they can penetrate the skin completely and the organs and everything else, and we get diagrams and pictures of the bones, okay? Gamma rays can go all the way through you. They're brilliant. They can penetrate just about anything, okay? So that is, what that shows me is the higher the frequency, the better its penetrating ability, okay? Lots for you to have taken in today. Let's look at a quick question. We're not going to spend too much time actually answering this because we could be here till Christmas, but this is the type of question you need to be able to answer. Says to you, give an example of the use of each type of electromagnetic radiation. First one is gamma rays, which we started with we ended with gamma rays, so we're going the other way around. Gamma rays, of course, are used in medical equipment to sterilize medical equipment. X-rays, used to image bones and to take pictures of bone structures and to know if somebody's got a broken bone, that sort of thing. Ultraviolet light, used in forensic situations. We used to know if there's been blood splattered or that sort of thing. Infrared, sorry, I missed out visible light. Visible light, well, we need visible light to see the world around us. Nice and simple. Infrared, used to see images according to their heat signatures. So places where we can't necessarily see something because it's too dark. All right, so it's nice for things like night vision goggles. Okay, so the military has use for those. Microwaves to cook our food. Cell phones. Radio and TV waves, which fit in the same category. Listening to the radio, getting television signals, all of those sort of things. Nice and easy. All right. We have already spoken about the penetrating ability of our UV radiation, X-rays, and gamma rays. Remember, the higher the frequency, the more likely they are to penetrate. Okay. Now, question 4 says to you, indicate the penetrating ability of the different kinds of EM radiation and relate it to the energy of the radiation. What that means is, what I'm wanting here is you don't need to go, well, radio waves have a high, you don't need to go through all of them, but this is where we need to get. Radio waves have a long wavelength and a high frequency. Sorry, low frequency. That's the other way around. I'm hoping you all realize that. So it's a long wavelength and a low frequency. That means they have a small amount of energy. We're going to talk about where we calculate the energy in the next, after we've taken a small break, okay? That means small penetrating ability, okay? Radio waves get absorbed quite easily by mountains and all sorts of things. It's also why you sometimes struggle to find cell phone reception, okay? Because your microwaves have very bad, don't penetrate as well as X-rays and gamma rays, and you'll know that if you're driving somewhere and you go through a valley, sometimes you really struggle to pick up your cell phone, okay? Or at home, if there's lots of buildings around you, you can sometimes struggle to pick up a cell phone signal. It's because it has a very small penetrating ability. So it's not going to travel through buildings and that sort of thing, and radio waves don't generally do that. However, we get to the other end of the spectrum where now we're looking at our gamma rays. Okay, they have a very short wavelength and a very high frequency. Let's change it so that it doesn't look like that's one word. They have a high frequency, which means they have a very high energy. And that high energy gives it a big or a great or a large penetrating ability. And essentially, a good way to remember this is frequency and energy are very closely related to each other. So if a wave has a very high frequency, it has a high penetrating ability. If it has a very low frequency, then it has a very small penetrating ability. Okay? Last one for now. Why do we need to protect ourselves from ultraviolet radiation from the sun? Sounds like a bit of a stupid question, doesn't it? But you know what? The whole point of your science curriculum, and this is what makes it so nice, is we want to put what you're learning in the classroom into context for you, and for it to be something that you can take out into the real world. This is a big thing. Ultraviolet radiation is so bad for us, okay? Nothing wrong with getting a tan, okay? Really nothing wrong with it, and it's important that we do see the sun. We need to get vitamin D from the sun. But when we are overexposed to ultraviolet radiation, because remember UVA can penetrate the skin, it can cause skin cancer and other skin-related diseases. It also can cause premature aging, so it makes you look older than you actually are. And I know as teenagers you go, oh, that would be wonderful. But you know what, as you get older, you don't want that. You don't want to be looking like you're 60 when you're only 40, okay? Just isn't cool. But the point is we need to protect ourselves. And we do that by using sunblock, sun cream, and UV protective clothing. Okay, making sure that our clothing can help us as well. Because it doesn't help us if we dressed like an Eskimo, but actually the sun can go straight through it. Okay? We need to protect ourselves from it. That also remember, guys, that means even on a windy day or a cloudy day, you can still get burnt from the sun if you're near water or on sand, because the sun reflects off it. Okay, very, very important. Now, wow, we've done a lot of work in this last session. So, we're going to take a short break, and then when you come back, we're going to look at the calculations that we need to work with for electromagnetic radiation. So get up, get a glass of water, we'll see you in a couple of minutes.